Þá bjóðum við velkomin til þess að halda smá tölu fyrir okkur notkun og prófun af blönduðum stáli í erfiðu umhverfi. Testing use of alloy steels in harsh environments. Vagn Hansen first.
Thank you. Yes, I'm from the Corrosion Metallurgy and Concrete Department, Forsk Technology in Copenhagen. And I was given the topic of stainless steel in harsh environments. And that's quite a challenge. That's a wide area to cover, because any environment which is able to challenge the resistance of stainless steel would be harsh. So we will talk about what is the challenge and which examples can we give on conditions which stainless steel wouldn't meet. And for stainless steel and other corrosion-resistant alloys, the resistance lays mostly in the passivity of the material, the surface layer which can protect the material. And the margin of this protection might be large, but the limit is sharp. And I needed a picture for that, and I wanted a cliff. And as you may know, we don't have that many cliffs in Denmark. So I looked to Norway and found the Preikestolen, which would be a good example, because the guy standing here is safe at the moment, but he doesn't have not much of a margin before he falls. It's a disaster when he uses up his margin. The other guys here are more safe. They have an ability to move a little before they hit the edge. The topics that I'll go through is something about the resistance, how to predict the resistance for a certain media, and what is going to make the conditions worse and what is going to improve these conditions in relation to corrosion. Some examples of harsh environments: stagnant tap water in Denmark might be harsh, concentrating chlorides giving stress corrosion cracking. A little about geothermal energy plants. I don't have that much experience, so it would be a general overview, and I'm confident that there will be more in that topic later today. Something about the special concerns for wells, and something about corrosion testing. The passivity of stainless steel is, as I said, in the chromium oxide layer on the surface, and the thickness of that is only 20 to 50 angstrom. And I don't know how you feel about that, but it's hard for me to imagine how thin is that. And the picture or the model that we usually use to describe that is to go into Copenhagen, where we have a church tower called Rundetårn, where we can go up, and if we bring a sheet of paper and place it on the top, then the approximately 35 meters of tower would be equal to 1 millimeter of stainless steel, and the paper would be equal to the passivity layer. So as you can see, it's very thin, and you will damage it at some point. Chemically or mechanically, you will damage this protection layer. And the real stability of the material will be is the material able to repassivate, to generate this again fast enough to avoid corrosion attacks. The primary parameters that we look into to see will that be the case or will we have corrosion is to define our media, our basic media, by the temperature, the pressure. Will it be gas? Will it be wet? Will we have a certain amount of salts or chlorides? Will we have other corrosive or inhibiting species in the media? Will there be oxygen or other oxidizers who can act as oxygen? What will the pH level be? That we need to know to define our media. And if we have increase in temperature, as it's shown here. When we increase temperature at a certain level of corrosivity, then we will need more stable or higher alloyed stainless steel to withstand that without having corrosion. And where do we get this information? Yeah, we have databases. We can get it from data sheets from the suppliers of materials. There's corrosion tables where we can go in and see for a certain simplified media, how will a certain alloy function in that, but have to be aware that corrosion tables are usually very much simplified. So you have a could be okay, but you always have to check by other means too. Other sources, yeah, we have diagrams for pitting. You know, when we have a material protected by a passive layer, then it will usually be localized corrosion that is the most challenging corrosion form. And local corrosion would be pitting, small holes in the surface growing to create perhaps a leak in the end. Or it would be crevices where we have weld defects or material in a flange connection, creating a crevice where corrosion will initiate. And we have simplified diagrams like this one for the corrosion, critical pitting temperature, the temperature where we can bring a material in a certain chloride solution before it starts to make pits. And we have these curves for different types of stainless steel. And as you can see, if we choose a certain chloride level, 0.1 percentage of chloride, then we can see that a 304 stainless steel will not be able to go above some 30 degrees C before we have pitting corrosion. 316, then we are at 55 or something like that. And if our temperature is higher, we need to have a higher alloy, for example, this duplex stainless steel. But we also have to be aware that this is laboratory tests on prepared surfaces, usually from the steel supplier who wants his material to act as at its best. So it's carefully prepared surfaces tested in the laboratory. And the same goes for testing for stress corrosion cracking, where we get not pits, but we get cracks growing into the material. And in fact, in the laboratory, we can have it growing as fast as 1 millimeter per day. So it would be very critical to have that kind of corrosion. And what we see in this diagram is that if we have evaporation, which will increase the chloride level, then we will not be able to go above some 50 to 60 degrees C before ordinary 304, 316 stainless steel will start to form cracks. And of course, higher alloy steel like the duplex stainless steel will be able to take a higher temperature before cracks will be seen. We also have something called iso-corrosion diagrams. That applies for acids, where we have general corrosion, where the passive layer is continuously dissolved in the solution. And in that we can have lines which says 0.1 millimeter per year, and we can select a material which will be below this lines for a certain amount of sulfuric acid in this diagram. And we can see that if we go to 40 degrees C, or sorry, 40% of sulfuric acid, then this 254 SMO will not go above 40 degrees C before it hits the 0.1 millimeter per year. So we have this different kind of diagrams and information to choose an alloy which would have the ability to meet this harsh environment. Oh, sorry, that was a line I intended to show. Come on. But that is laboratory. And in the real world, there will be something which will increase the risk of corrosion and other which might decrease the risk. Increasing, if we have oxidizers, if we have flow, which might be a high flow with particles, or it might be a low flow where you can get concentrated conditions in some areas. It might be surface defects and irregularities, as examples here from a typical school book on welding. All these defects that might happen in a welded area, and which might lower the resistance of the surface, where we have arc strikes, we have weld spatter, we have embedded particles from tools or such, we have heat tint from oxidation, all things that lowers the corrosion resistance from the laboratory data. We have some help from standards, at least in aqueous, that is water systems. There is a standard called 12502-4, which is an old German standard which has become a European standard. And it says that the likelihood of pitting corrosion and crevice corrosion is increased by welding defects, filler metal sagging, incomplete root patch, edge misalignment, and so on. But this standard is only raising a flag that you might have a problem. You don't have a standard that says you can't have it. It's for the people who are specifying the job to say, oh, we have a standard that says it's not good. We need to write that we don't want it. We want a clean surface. We want no welding defects, or as close as you can get to that, of course. We also might have microstructures forming in the material from the heat during welding. At least the arc welding processes where we have melts, we will have different structures from forming in the weld material. I'll come back to that. And the heat might transform some of the stainless steel, giving us intermetallic phases like the sigma phase seen in this structure. It will give a significantly lower corrosion resistance. And the reason is that chromium is going into these particles, and you will have too little chromium around these particles to keep up the resistance of the material. What might help you is if there are inhibitors in the media, something which will sort of block the corrosion process. Or if you have something, you might have a corrosion depending on oxygen. But if there's something which will take the oxygen out of the solution, then of course the corrosion will not happen. And I think you know that if you have a central heating system in your house, you will know that when you put on new water, the oxygen will go in and it will be consumed by the steel surfaces in there. And once consumed, there's no oxygen and there's no corrosion in this system until you put on new water. So anything in the media which will consume oxygen will lower the corrosion resistance below what you predict from the diagrams that I have shown you before. About the oxidation, this standard, it's 12502, says that oxide films and scales can be formed and highly increase the likelihood of pitting. You could say that this is a weld in a stainless steel without any protection at all, full oxidation of the weld metal and of the heated surfaces, the heat affected zones on the side. And maybe you can't see it, but there are a number of pits and a few leaks in this area. I think this one is a pitting which is going all through the material. So it says that if we can keep it below straw, it would have a chance, unless the corrosion conditions are too harsh even for that condition. So we have something like a criteria here. But you might know that in the workshop or on the construction field, you will get into a discussion which kind of straw are we talking about. The guy who is welding would say, oh yes, this is like a very yellow brownie straw, and I met that. And the guy who is controlling would say, no, this I'm going for a slightly lighter straw. So you need some references for that. And I've not brought that today because I usually talk a lot about these reference charts, but they are available where you can select a certain degree of heat tint. Specify that, have it for inspection and acceptance criteria. But here you can see that a better purging than this will still give corrosion problems. The weld is perfect, but we still have pitting corrosion in this oxidized, this colored zone from the weld heats. And on to some examples of harsh environments. And this, the stainless steel says this was too harsh. You can see we have pitting corrosion, we have a lot of rust formation around this weld. And in a cross section you can see how it's this small hole in the surface is growing into a big cavity, and the weld metal is like a sponge after due to corrosion. And we even have a pitting here, which is in the heated oxidized zone. So the harsh environment here is stagnant tap water. It's a water supply system where they take ordinary water from the tap, but they don't use that much water at all times. So sometimes it's stagnant. There's no flow for perhaps a week or so, and that's enough to cause this problem. And as we talked about before, welding defects as lack of penetration here, the heat affected zones. You can't see it for us here, but you can see up here that it has definitely been colored after welding, and that is causing problems which might have been overcome if we have had a higher alloy stainless steel and a better weld condition. Another example, this is a dryer where we have a product with chlorides, with salt in it. It's wet, it's going to be dried, so it meets hot air in this tank or chamber. And on the surfaces, this wet material is sort of depositing and drying up. And in that process, chloride level is increasing into a level where we can have stress corrosion cracking. And as you can see, that's a very bad situation because these are numerous cracks going branched into the material. And repair, yeah, that's cutting somewhere up here and somewhere down here because this area is totally destroyed from cracking. Again, there's a relation to welding because the stresses along, there's a weld here who has been polished off. We also have a weld here, and the stresses around these welds, you can see the weld metal like this. The stresses here are the driving force together with the chloride level and the temperature in this chamber. Once the material has dried up, so that it's totally dry, no humid in the deposit, then in fact there will be no more corrosion. So if we have a weld up here where everything is dry, it's safe. But exactly here where we have the wet product drying up, we get all this cracking. Again, you can take a material with a higher, in this case, level of nickel, somewhat more chromium, and it will be able to work in this process. As I said, I'm not an expert on geothermal conditions, so I have to borrow from the literature. And what I have found is that the critical parameters that is specific for geothermal applications is salinity, the pH, any aggressive constituents in the brine, which might be H2S. It's whether there is oxygen or not, and the temperature at a given part of the system. If we have conditions with very low salt content and approximately neutral pH, then we have very little corrosion. Uniform corrosion means that we lose a little of the surface all the time, but below 0.3 millimeters per year. So you can control that by adding a little more wall thickness in your system, and you will be okay for a number of years. So low alloyed steel is what we can use there. But if the salinity, the amount of salt is increased, pH might be lower, then we must have higher alloy materials. And like some of the media that we have just discussed, common stainless steel might not be enough. We might risk pitting from the chlorides. We might have stress corrosion cracking. We might have crevice corrosion. So usually, if we have high salinity, then you have to go above ordinary stainless steel. So even the duplex stainless steel might not be enough. This is from an autoclave that is high temperature, which also could be present in geothermal brines, high chloride level. And in fact, there was a crevice below a plate in the autoclave which would concentrate the chlorides to a level where we have stress corrosion cracking and selective corrosion. In this attack, it's the ferrite part of the stainless steel, which dissolves in the corrosion process. So there will be a limit for temperature, salt, chlorides for this more common stainless steel. Even for higher alloyed materials like this alloy 31, which is pretty close to another Sanicro 28, which doesn't have that much molybdenum, but still, those are higher alloyed materials, and they would be suitable for medium and for low salinity and still neutral pH. Higher salinity, the temperature for this alloy would be 100 degrees C. Above that, we will have crevice corrosion if there are any crevices in the system. But of course, you can choose higher alloyed, more resistant materials like the nickel-based alloys, alloy 59, Hastelloy C276. They would be perfectly safe, but also very expensive. Perhaps 10 times what you would pay for a stainless steel per kilo. So it will be expensive to be safe. From another source, in the materials performance research project done, I guess, here on Iceland, on corrosion risks in gas separation systems, where we have H2S, we have CO2 gases dissolved in the brine, but which is good for stainless steel, no chlorides in this solution. The pH might be relatively low. The risk that we have to address on this is whether there will be general or localized corrosion. The H2S, we might consider whether there will be a risk of hydrogen-induced cracking. but that would only be for martensitic material. That's only for hardenable materials that we can risk that. So if we go for stainless steel or austenitic stainless steels, we will not see the hydrogen-induced cracking. We have to look into the stress corrosion cracking, not from the chlorides, but from the H2S. There would be a risk of corrosion in the weld zones. But the test done for this particular system was that the 316 stainless steel and the duplex 2205 would perform satisfactory. No general corrosion, no pitting, no stress corrosion cracking. So due to the level of chlorides, an ordinary stainless steel would apply for this one. I have one example though, which is related to geothermal conditions. It's from a heat pump, a heat exchanger on a heat pump, and as the conditions was to be without oxygen, ferritic stainless steel, the grade 430, which is 16% chromium steel, would be safe, but only if there was no oxygen. And in this particular system, they had some problems during the commissioning when they are starting up. So it was left standing still. Oxygen entered the system, and the result within a year was that this heat exchanger could be cut out. There was pitting corrosion everywhere in these tubes. About the special conditions for welds, ordinary arc welding, where we have a material which is melted and solidified, we will have a cast structure. And a cast structure means that we, to some extent, will have a distribution of alloying elements. Chromium will not be the same in this structure. There will be areas with higher chromium and lower, the same for molybdenum, and that will affect the corrosion resistance of the weld. I will have an example in a little while. In the heat affected zone, we will have grain growth. Not so much on the austenitic material. It's hardly visible that there's anything happening here. This is a longitudinal weld in the tube, so that's also weld metal. In other materials, it's different. This is a duplex stainless steel, and we have the heat affected zone here. We have the fusion line going like this, and as you can see, the material here is in heat affected zone is very similar to the weld metal. It's has been the original structure in the plate has been dissolved. It would have been a two-layer ferrite austenite like we saw in the corrosion example before, but due to the heating, it has been dissolved, transformed fully into ferrite, and the cooling afterwards had given a transformation which gives a structure which is similar to the weld metal more than to the base material. And depending on how the distribution is between ferrite and austenite in this zone, there might be a great difference between the resistance of the heat affected zone and the base material. The weld metal will be over alloyed, so there's a bit of help from that. And of course, as we saw with stress corrosion cracking, welds will tend to give stresses in the weld zone, tensile stresses in weld metal, and in the coarse-grained heat-affected zone, there where we have the risk of stress-induced corrosion, like stress corrosion cracking. So welds will generally be a weak point from a corrosion resistance point of view. And it can be seen very clearly in this piping, this tube or flange connection, which has been applied in sulfuric acid, hot, strong sulfuric acid, And as you can see, the general surface is slightly attacked, like we saw in the iso-corrosion diagrams. Something will happen, but very slowly. But the wells, they are clearly attacked to a much deeper level than the material. And as we can see here, at some point, we will have a leak in the weld zone. And that's due to the partitioning or the segregation of chromium and molybdenum in this structure, like this. One of the ways that we can sort of quantify this is by making a corrosion test. And one is very popular to sort of rank different stainless steel, and that is putting them into a ferric chloride solution and measure the temperature that you can go up to before we have pitting corrosion. And if we do this, put these results into a logarithmic diagram, we can have a equivalent for the corrosion resistance, the chromium, the molybdenum times 3.3, and 16 times the nitrogen content. Sorry. Then we will have a line saying that the higher the equivalent, the higher the temperature we can go to before we have pitting in this test solution. But as you can see, if we do the same with weld metal, and this is orthogonal welding, that is without filler, then we can see that it will definitely be lower. And at some point, it will have a very large deviation from the base material. And again, that is due to the partitioning of the alloying elements. The distance here might be larger or smaller. If we have very fast welding, fast cooling, then the distance will be low. The weld metal will be very close to the base material. But more heat, larger pools, then we will have a variation. This is larger. But from here, which is almost like the 904L, then above that we cannot have welds which makes the base material resistance. And what can we do then? We can add filler material. And the 6% molybdenum steel, the 254 SMO, which is approximately here, will need to be welded with a material up here in order to have the weld metal being dragged up to meet the base material. So in fact, it's welded with an Inconel 625 filler material to meet the base material resistance. We might also have something in the structure which made it sensitive to corrosion. I'll come back to that in a moment. We might have galvanic couples, which are some part of the structure will be noble to others, and that would cause corrosion to happen. We might have problems in the duplex stainless steel with phase balance. If we have too much of either ferrite or austenite, we will have corrosion resistance which is not meeting the base material. This is a traditional welding problem in stainless steel. Too much carbon in the steel will cause trouble with sensitized material. The carbon would be on the grain boundaries, forming carbides with the chromium, and around these chromium carbide particles, chromium will be depleted, and we will have corrosion which makes the material fall apart like sand grains, as you see here. And if we go into a diagram showing what's the problem or how big is the problem, there has been made test with a Strauss test, which I'll describe in a moment. But that's boiling sulfuric acid with some copper addition. And if we are able to boil it for 24 or 36 hours in this solution, and it will not give cracks if we make a bend test afterwards, then it's good. Sorry. And what we can see here is that if we have 0.08 in carbon, then approximately half a minute at 800 degrees C would make the material fail this test. And unfortunately, that's the limit. If you order 316 stainless steel without the L on, then you can have 0.8 in carbon. That's the limit for that designation. Usually you will get better, but in fact you haven't ordered it, so you could also get something which is that poor. And it's very problematic to weld without being in this field for more than half a minute. If you choose to buy with the L, the limit is 0.030, so that you have like 7-8 hours before you have problems with that. And that's accumulated time. So if you weld, make a defect, grind, weld again, then you might at some point reach these 8 hours. But I think you should go here before you weld any further if you have that problem that it will take you 8 hours to weld this system. So usually materials with low carbon, we don't see this kind of problems. Oh yeah, to implicate. But we can test if we have a correct corrosion resistance in the material. To take it in general, we can, of course, take a sample of what we intend to use, put it in these conditions, see how it goes. That would usually take a lot of time before we have the result. We can have test solution which sharpen this and we get a result a bit faster. But we can also make tests in the laboratory where we put on some potential to increase or to control the corrosion conditions, and that way find out where is our critical pitting temperature, where our crevice limit is, and by controlling the temperature or the potential. Oh, sorry. The potential is the fuel for the corrosion, and we can measure the potential giving trouble at a fixed temperature, or we could have find the temperature at a fixed potential. That's the possibilities. We can do the ferric chloride test that we saw in the diagram before, test in actual media or this ferric chloride test. And we have the Strauss test for intergranular corrosion, boiling sulfuric acid, copper sulfide, copper chips, 24, 36 hours depending on which standard we apply, and then make a bend test to see if it cracks. And that's also possible if you have had some fire which would bring your material on to the critical temperatures for a number of hours. Then you can do a test afterwards to see if it has been damaged by this process. This is some laboratory equipment for the electrochemical testing, where we have the solution in a chamber here. We have cooling water around to control the temperature, and the sample that we are testing is placed here and here, so that we can and there's of course an opening to the solution on top of it, and we can apply a potential, and we can measure when does the current increase in this system. And when the current increase, we have a pitting which has been activated, and we have the temperature or the potential, whatever we measure. The G48 is a standardized test for and used very much for welding procedures in stainless steel and other corrosion-resistant alloys. We define for a certain material that it has to be able to withstand this ferric chloride test to a certain temperature, and depending on how successful the weld has been, it will fail or it will pass this test. And this example show a sample which has passed. There are some pits. The evaluation is that the weight loss in the test has to be within a certain limit, and there must be no visual pitting examined in a microscope at, I think it's 20 or 40 times magnification. You will not be able, or you should not see any pitting corrosion. And here we have had some help from dye-penetrant testing to find the pitting. So this one is failed due to pitting from the test media. And this is the cap side, I think, and no problems with corrosion there. We saw before that the test on the geothermal plants in Iceland, that there has been tested at high temperatures and high pressures to see which materials would be sufficient there. And in fact, that's something that you do in autoclaves, and we have recently acquired a large autoclave laboratory so that we can test specific media at high pressures, high temperatures, and with media meeting the actual conditions. Also full-scale testing of up to a certain size of piping or such. We can go to 750 bars, 750 degrees Celsius. I'm not quite sure. It's the highest in gases and lower in solutions. We can handle H2S, CO2. Those were the ones were considered in the Icelandic work. Nitrogen. We can have high flows. We can add chemicals, and we can do electrochemical tests under these conditions, and as I said, full-scale tests. So we would be able to help out if you want to test solutions for these very harsh environments where we have high temperatures, high pressure, and perhaps a very corrosive environment. So to summarize, detailed knowledge of the media and the corrosion mechanisms from experience. Might be bad experience, but you have learned from it. Data review or tests to allow for an optimized selection of materials. That way, you can stand here and you will know how large your margin is and how safe you are. Thank you for your attention.
Eru þið einhverjar spurningar fyrir Vagn Hansen, gjör svo vel?
Surface treatment of the steel.
Yes.
Pickling or glass beading effects.
Pickling, yes. The best would be to electropolish. From corrosion point of view, electropolishing would be the optimal choice. Below that, pickling. Because pickling will remove any foreign particles, any slags that could cause, it will even take micro crevices from the surface, and that way it will be more resistant. Of course, you have to do it in a way that you don't increase the roughness too much. So a proper pickling would be the best. And you asked for blasting. I'm not so keen on blasting because it would be okay to remove some large particles, but it will also smash some into the surface and keep them there. Glass blasting is very nice for our eyes, but not for corrosion resistance.
So it will not regenerate this
Yeah, yes, that's the point in pickling. You get a fully clean surface, and then it will generate its passive layer within short time. We usually say that a clean surface, either pickled or it's ground, polished, then it needs some 10 days to a fortnight with ordinary humid conditions. Then the passive layer will be at its thickest condition, that will not grow any further. So you just have to keep it clean for that period. And if you can't do that, you follow up on the pickling with a passivation based on nitric acid. Then you generate a passive layer immediately in the process. So.
Another question.
Yeah.
Temperatures and the escalation of corrosion. I mean, would there be any sense in cooling items of stainless steel to reduce corrosion?
Yeah. You would see that if you have a certain system, the cold part, which might be below 10 degrees C, it would take much more chloride to initiate corrosion compared to, say, 30 degrees C. So the only way that temperature can help you is if you go up in an open system and boil off oxygen so that you have an oxygen-free system. Then temperature helps you. And that's what you do on boiler waters. You take it through a deaerator where temperature and vacuum takes off oxygen, and then it's safe to put into the boiler.
Flere spurningar?
Welcome.
I have one question. When you use an orbital welding machine,
Yeah.
you don't have a filler material,
No.
then this weld would be lower in corrosion class than with filler material.
Yes, but you usually, when I think orbital machines, I think very thin walled piping, and it's a very fast process. So our experience is even with a very, very qualified welder, hand welder, the amount of weld metal will be lower in the orbital welding. The amount of heat tint on the sides will be lower in the orbital welding. So it's possible to do a very, very good hand weld, but it will always be slightly better in an orbital weld.